Our afternoon session now. Please take your seat. So our first talk on this afternoon section is by Chiara Mocenni from the Department of Informatics, Engineers and Mathematics from the Università of Siena, Italy. And the title is Bridging Self-Games and Cooperation, Evolutionary Games on Networks. So please, Chiara.
Okay, thank you very much. Thank you, George, for inviting me. Thank you, everybody, to be here. And so I will talk about consensus, cooperation, and games, and try to make a connection between these three topics and three ideas. So in general, emergence of cooperation is a very hot topic in the scientific literature in the last year, and many people worked also from the evolutionary game approach, using an evolutionary game approach on these topics. And many people have been also presenting their research in these biomath conferences, like I don't know, Martin Novak, George Pacheco, but also Fabio Chalub, Max Souza. Many people are interested in working in this topic. My goal here is more focus on cooperative consensus. So I will also introduce the concept of consensus, which means that essentially all players cooperate, joining to a common goal. Trying to reach a common goal. So what I use as a mathematics to tackle this problem is an extension of the well-known replicator equation that Fabio introduced also before, that I have done in the last 2 years, introducing also dishomogeneities in the population structure. So in this way, we are able to get a kind of a weak cooperation instead of strong or full cooperation. And in this way, we also have the possibility to introduce the concept of self-games in order to get some kind of consensus to a weak or strong cooperation solution. So I will also discuss the existence and the global stability of the cooperative steady states. So what is consensus? Imagine to have a dynamical system where you have a structured population of a finite number of interconnected agents. And imagine that those individuals, that there are in the problem individual or common goals. And each agent dynamics is characterized by a state variable xv, where v indicates the agent. And of course, this variable is changing over time due to its due to the interactions that he has with the other individuals. So in general, we have this kind of this kind of dynamical model where, of course, the function fv at the right-hand side of the equation depends on the states, but also on some adjacency metrics, which represents the structure of the population. And so the possibility that two individuals are connected or not in the game, or in general in the dynamics. So the consensus in this framework is the convergence of all xv to a common value. On the other hand, we can talk about cooperation. So what is consensus in the framework of cooperation? We might have dangerous consensus, like, for example, dictatorship. I mean, for example, in a social context, we may have a dangerous consensus. We might have selfish consensus when the best is for to get the individual maximum reward, or maybe also the interest of the whole, which is, in this case, I call cooperation or cooperative consensus. In general, see, for example, in the case of a common goal, common goods, or environmental protection, or climate change, or other problems that involve general expenses for the population, selfishness and cooperation do not match. Most of the cases, they do not match. So, in general, what the people are looking for is to reach a cooperative consensus, which may be a desirable solution for the population. Somehow, we can also see this problem as a control problem, where we try to move the dynamics from a bad, in case that it is dominant, to a good consensus steady states, in case that we want to drive our population to a good solution. Then, game theory. Game theory deals with decisions, and players are the decision makers. The decisions are the strategies, maybe everybody knows, and each player gets a payoff depending on its own and the other player's strategies. So in this framework, we can, for example, discuss the problem of cooperation versus defection, which is also a well-known topic in game theory in general and also in evolutionary game theory. So, for example, we might have two strategies, cooperation and defection, and we may build a payoff matrix which represents the reward that each player gets depending on his own choice and on the choice of the other player. In the mathematics, some mathematical details are the following, that we transform the payoff matrix in case that we only have two strategies to a diagonal matrix by appropriately transform without changing the preference of the strategies of the game. So we can work with the diagonal matrices. This will be clear later. Now, I want to move from game theory to evolutionary game theory, just to introduce the language that I'm working on. So game theory essentially is a static model. So the game is played once, only once. But more often, the game is repeated in time and between many individuals. For example, when we have a large population of individuals that interact each other. Now, the players in general are indistinguishable in the population, except for the phenotype, which is represented by the strategy. For example, a genetic trait. What is changing in time is actually the distribution of the strategies over the population. So the individuals essentially do not change their mind during their lifetime, but at the level of the population, the fittest group will reproduce faster, so it will survive and eventually it will win. There are many different situations, but in general, the fittest group will be stronger and increase in time. So this means that the population reaches a Nash equilibrium, which is also always a steady state of the replicator equation. This is actually the well-known replicator equation, and this framework is the evolutionary game theory. Now, what I proposed in the last years is to move from this framework to an inhomogeneous situation. And in particular, I tried to work to get a mathematics describing the dynamics of a finite population of individuals instead of a very large population, introducing a structure into the population, which means to have, for example, a graph which is describing the kind of connections that individuals have one with the others, and not assume homogeneous games. So in this framework, we see that each player may also play mixed strategy. Because in general, the phenotype I have told before corresponds to agreeing to choose a pure strategy. I have blue eyes, I have this kind of characteristics, and I don't change it for all my life, for example. But in case of a distributed system where each agent can have its own dynamics and changing its dynamics, its choice over time, we may have also that any single individual may have also a mixed strategy, which means that, for example, he might be altruistic and selfish at the same time with some distribution of these two characteristics, or he may have defective at the same time and cooperative at the same time. For example, 50% defective, 50% cooperative, okay? Or all the other potential distributions. So these are known evolutionary games on graphs, and I will try to discuss about this equation a bit more. So we can read the variable xv now as the propensity of player V towards strategy C. For example, the propensity of a given individual to be cooperative. C means cooperation. And of course, 1 minus xv is the propensity towards strategy D. The payoff matrix, which is a diagonal payoff matrix, where sigma chi and sigma d are respectively the payoffs for cooperation and defection, is the payoff matrix of player V. Now, of course, this matrix may depend on V also. Okay, so not necessarily all players have the same payoff matrix. But assume for a moment that they share the same payoff matrix. Now, the EGN equation is the following, which has a structure very similar to the replicator equation. Here, you see even from the talk before. But this is multiplied by delta PV, which is the difference between the two payoffs from getting cooperation or choosing defection, multiplied by the elements of the adjacency matrix A, which means that if two people, V and W, are not connected according to the graph described by the adjacency matrix A, they will not play any game. Okay? So this contribution to the payoff, which is actually the sum of all the contributions from all the games, will be 0. Okay? So just to give you some more detail on this equation, notice that now we have a number of equations corresponding to the number of players. So the order of this model may grow fast, depending on the order of the population. So we have also tried to study the model reduction in order to reduce the number of parameters of the model and also to reduce the order of the model by using the concept of lumpability of a graph. And we tried that in some case we can collapse groups of nodes in order to reduce the order of this model. Anyway, regarding this equation, of course, we can easily see that xv will increase if delta pv will be greater than 0, because this term is always greater than 0, so the growth of xv depends only on this difference, delta pv. So in this case, strategy C is better than strategy D, and strategy C is better than xv, so xv will tend to increase. And xv will decrease if on the contrary, delta PV will be less than 0. Of course, we have xv equal 1 and xv equal 0 that are steady states for this system, and also all the other steady states such that delta PV is equal 0. We concentrate on 3 kinds of steady states. All D, we call X all D, and briefly all D, the states for which all players will choose strategy 0, which means that they will all defect in time. I mean, will defect at the steady states. X all Chi equal to have all players choosing strategy C. In this case, we have that the steady state is X all Chi. And finally, X all M, where the vector is composed by all the same values, M, 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 where M is sigma D over sigma C plus sigma D, which is a mixed steady state. But considering that in this case, all players have the same mixed steady states. Of course, this equation has much more steady states. For example, all the steady states that are combinations of these values, 0, 1, and M. So there are many, many other steady states, but all these other steady states are not consensus steady states because all the players have different components of the steady states. So just to give you some examples, in the prisoner's dilemma game, in the traditional framework, we have actually dominant strategy, which is defection. Defection is a Nash equilibrium, and cooperation is not a Nash equilibrium. So defection is preferred when player 2 cooperates, and defection is also preferred when player 2 defects. This is well known. Another kind of game that has been used also to model the problem of climate change and other conflictual situations among people is the stack hunt game. That is essentially a bistable situation or coordinated game where you have that the best answer to cooperation is cooperation and the best answer to defection is defection, which means that the 2 individuals will essentially choose the same solution. And this will produce a kind of dynamics over time, which is a kind of complicated situation because the final value of the dynamics will depend essentially from the initial conditions. Okay? It can be cooperation or defection depending on the initial condition. And finally, I also talk about the chicken game, which is the opposite, is similar to the hawk and dove games, where you have a coexistence steady state, which is a Nash equilibrium. No one of the pure steady states is a Nash equilibrium. Essentially, in this game, we have that defection is preferred when player 2 cooperates, and cooperation is preferred when player 2 defects. So this means that the 2 individuals will make different choices, opposite choices. And this will produce in the population a mixed solution, which is also a Nash equilibrium. So for example, in the case of EGN, where we have a network under the dynamics, so imagine that you have this kind of topological structure of the individuals, and some individuals have a bigger or smaller initial condition, and they are connected somehow. Very, very generic, no assumption on the topology of the network. So the network topology is arbitrary, and you see that, for example, in the prisoner's dilemma game, the solution will tend asymptotically to all the consensus steady states. while in the two cases of the stag hunt game and the chicken game, we have that, for example, in this case, the convergence is to all D. All individuals will defect, but this is strongly dependent on the initial condition. Finally, in case of the chicken game, we don't have any kind of consensus, and maybe each individual will go to a different solution over time. So there is no consensus. Now, summarizing a little bit what I have said, I will say that, for example, for the stag hunt and chicken game, for both of them, the mixed steady state exists. But all M represents a consensus where players partially cooperate, but unfortunately, all M is a set. So it's never attracting steady states. Okay? So it's not possible to have a natural tendency of the population to converge to the all M steady states. Okay? So we cannot have a consensus. While we might have a consensus on defection or defection again, we don't have any chance to have consensus on the mixed steady states. Moreover, if we break the symmetry on the distribution of the payoff matrices to the elements of the population, which means that, for example, some of them we have a stag hunt and some other a chicken game payoff matrix, maybe we get some oscillations, but this is not very important for us, just to notice. So all chi is never reached in the chicken game. Sometimes all chi, when there exists a global attractor, it's not on all chi, but all D, for example, in the prisoner's dilemma game. And all chi can be an attractor only in the stag hunt game, but this depends strongly on the initial conditions. Okay? So now the question is, how cooperative consensus or weak cooperative consensus can be reached? For example, I mean here, all chi is all individuals of the population will cooperate 100% probability. Okay? In all M, they will cooperate in a mixed situation, according to some probability to cooperate. Now, in general, how people work to get a consensus in the population? Generally, there are economic outcomes. For example, some rules that are supervised, so some external mechanism that may drive the population to cooperate. Or more in general, we can say that cooperation more often is not necessarily the result of some economic outcome. May be due to some internal mechanism. For example, we can be aware of the importance of being cooperative. For example, as I said, in the case of environmental protection, we might have some awareness about the importance. So we try to model this kind of mechanisms through the introduction of self-games. So introducing a self-games means that a player is playing a game against himself. It's virtual game because there is no money exchange, either in the mathematical formulation. It's very difficult to transform this kind of self-rewards into economic outcomes. And the replicator equation on graphs, the EGN, will be modified according to this formula. So this is the old part where the difference on the payoff of the two strategies will depend on the other individuals of the population. And then we have one more term here, which is also depending on the difference of the two payoffs upon some transformation I will talk you in a minute. multiplied by the KV term, which is actually the degree of the node V. Okay? So we have a new term adding to the delta PV, which depends on the degree of the nodes and also on these two parameters, mu C and mu D. Mu C and mu D are essentially the new sigma, the new elements of the payoff matrix according to this kind of transformation. So we assume that the elements of the diagonal matrix of the self-game will be equal to the degree of node V multiplied by some parameter mu C. And the same for the payoff for the defection, for example, in this case, will be equal to the degree of the node V multiplied by the parameter mu D. So you can notice here that the matrix B is not constant for all players because it depends on the degree. So assuming that each player has a different degree, we might have that the sigma are different. So there is, and moreover, notice that the presence of this term here means that somehow this term must be comparable to this term. So the degree is somehow taking into account the strength of the payoff from the connection to the other players. Okay, so now we can discuss in this new framework, upon the introduction of safe games, we have some results on the existence of the mixed steady state, which is the weak consensus. Now, I will not report many details about this, but I will just report here some picture where we try to vary the two parameters, mu C and mu D, and put different colors in case that the mixed steady state exists or not. Okay? So we can see, for example, here that also in the prisoner's dilemma game, we have some regions, the green regions, where the mixed steady state exists, at least. While we know that in the standard framework, the prisoner's dilemma game is a dominant game, doesn't have any mixed steady states. The same happens for the stag hunt game, where we have these mixed steady states. And we know that in this case, the mixed steady state exists also for the standard case. And the same happens for the chicken game. So we see that essentially these two green regions are represented by the fact that the two parameters, mu D and mu C, are both big, or both big in absolute value. Okay? That must be somehow both enough strong in order to counteract the influence of the other players into the system. Okay? So something changed. This is a simulation I have done in order to show you that something similar happens also if we break the symmetry, in sense that we don't assume that in the standard game, the game that each player is playing against the other players is not the same for all individuals. So we split the population into two groups. Some of them will play the stag hunt game, some other will play the chicken game. And we see that also in this case, we have the mixed steady state existing. Now, but unfortunately, the existence of the mixed steady states is not enough to ensure that the population will reach the consensus, because these mixed steady states might be repulsive. So we need something more to be sure that we are able to drive the population to a consensus situation. Of course, we know that all C, so all individuals playing cooperation 100%, is always a steady state. Okay? So we have to study the stability of these steady states. In case of all M, we need also to study the existence, as I have said. Okay? So our next step will be to discuss about the stability of all C or all M. So strong or weak cooperation. So there are some papers. One of them is with George Subelli, is under preparation, where we studied essentially the existence. But now I'm just going to show you the most interesting results we get. In this case, I'll show you, of course, there are some theorems under this, but I don't want to go into the mathematical technical details about this. I just want to show you these pictures. Now, in this case, we are dealing with the prisoner's dilemma game. Okay? So we see that here you have the two parameters, mu c and mu d. And you can read this graph as follows. Okay? Blue color represents all C. Dark blue represents that the state xv is converging asymptotically to the solution all C. Red color means that asymptotically the values xv will tend to 0, which means that the population will get the solution, the steady state xv equals 0 asymptotically. And we see that, this is not obvious, okay? Because in the prisoner's dilemma game, to have all C is not natural, okay, in the standard framework. Moreover, we also have this region here where also the state all M is asymptotically stable. So it is an attractor. So this means that for these values of the parameter mu c and mu d, we have that all the elements of the population will converge asymptotically to the mixed steady states. And we also have this region. I didn't put any name here because here we have all the other attracting steady states that might be not consensus steady states. For example, they might be all the other steady states we have, of course, in the equation. For example, when the values of the steady states are not the same for all players. And moreover, there might be also some cooperation, defection, and mixed values. So we see that, for example, for the prisoner's dilemma game, where the sigma c is less than 0 and sigma d is bigger than 0, we have in the payoff matrix that each player is playing against the other individuals in the population. We have that all chi is reached globally when μ1 is bigger than 0 and μ2 is less than 0. So somehow they have different signs here. Okay? So there is a balance, must be a balance, and this balance must be strong enough in order to make the players able to change their choice. So cooperative consensus is reached when the self-game is opposite to the external game. And you see that, as I said, all M is also feasible for particular cases, combination of μ1 and μ2. In this picture, I report over time the dynamics of all the nodes of the networks here, and you can see that for these values of the parameters, all the elements will converge to the value 1. Now, these are the similar results for the two other kind of games, where you see in all cases we can find some region where the solution all C is reached, all D is reached, and all M is reached. So, of course, the shape of these regions is different for the different games, but we can find combination of the parameters where all these situations are possible. And, for example, in this case, you see that all M is an attracting steady state. So in this case, the population will converge asymptotically, not at global level, but at the level of any single element of the population to the mixed solution. So I'm going fast to the conclusions. I think, I hope, I have convinced you that cooperative consensus can be reached at the global level of some kind of global stability when self-games are present. Okay, so the presence of self-games is able to drive the population somewhere we really like. And moreover, cooperation can also be of a weak level, can also be partial, not necessarily strong. What we think is that self-games are able to model, for example, other non-economic factors like culture, awareness, and other kind of processes, mechanisms of individuals in a society. We can think of this problem as a distributed and unsupervised control. As I said, trying to move the population from one natural solution to another desired solution can be seen as a control problem. But now this control problem is distributed in the sense that we can think that the individuals have a position in the space, are located in different positions in the space. So they can be, for example, robots, or they can be other kind of agents that must adapt their behavior or their trajectory, their movements, according to the presence of all the other elements, agents in the system. And moreover, this control is not supervised, because there is not any function which is externally driving the population to the desired solution, but each agent is able to control himself just by means of the self-gain. So this is a kind of feedback. So we can also investigate these elements of self-gain as feedback in the control problem. And we want to prove the asymptotic stability of all Chi and all M by means of Lyapunov function. For the moment, we have only tried to do some numerical simulation and also use the Gershgorin disks, so some numerical methods to show the convergence to these steady states. But we are going to develop new mathematical methods, and we already have some results on this. And we also have very recently published the application of this model to the brain dynamics in collaboration with some neurologists, because we can think that the brain areas has the role of these agents that we are modeling with our equation, and they collaborate or not collaborate according to the information they are able to exchange each other. So we can think that there is some kind of network. Okay, the literature is full of results on this kind of approach, where the anatomical areas of the brain are connected each other according to some topology. But we are able to use our equation to estimate the parameters of the model in order to optimize with respect to some real data. In particular, they were functional magnetic resonance imaging data, and modeling the spontaneous brain functioning. Okay, so that's all. I want to thank Giulio Jacobelli, Dario Amadeo, Jean Moraes, and Zubelli, of course, and the project Science Without Borders, and that supported me to come here to IMPA to work for 3 years. And also this project on epilepsy that we are working on, financed by the Tuscany region. Thank you very much for your attention.